Hello everyone, I am Alberto Galasso. I'm a professor in the business school at the University of Toronto, and in this video I'm giving a short talk on my paper, When Does Product Liability Risk Chill Innovation? Evidence from Medical Implants. This is joint work with Hong Luo at Harvard Business School. The paper has been recently accepted at the American Economic Journal, Economic Policy. You can find the link to the paper in my webpage, and the link of my webpage is in the description of this video. So countries around the world have product liability laws that protect customers from defective and dangerous products. And cases involving product liability disputes tend to receive a lot of media attention because often they are related to big pain and suffering, and also because damages tend to be very, very large. For example, in 2017, General Motors had to pay about 2.5 billion in penalties as settlement because the ignition switch of some of their cars was linked to more than 120 deaths and 275 injuries. So the idea behind the research project that, and more generally the research agenda that Hong and I have, is to try to understand how is it changing these liabilities. So if we increase, for example, the damages that GM had to pay to 5 billion, or we reduce them dramatically, how is it these changes may affect the rate and direction of innovation, the innovation incentive of firms. So would we expect these changes to increase or decrease the amount of money spent in research and development? And would it expect these changes to affect the type of research projects in which firms invest? We think that this is an interesting question from an academic perspective, but is also a question that has kind of received a lot of attention from the policy arena. There are various policy discussions these days on how to design liability for new technologies, in particular technologies related to artificial intelligence and Internet of Things. Just to give an example, in February 2017, the European Parliament passed a resolution which there was recommendation to have a EU-wide legislation to regulate sophisticated robots, bots, androids, and other manifestations of artificial intelligence, and to establish legislative instruments relating in particular to the liability for their actions. And here the idea is that we have a current system of liability that works well with existing technologies. Think about cars, for example. If I have an accident with my car, we have a sense now how to deal with that. We know that my insurance is likely to have to pay to someone if someone is getting injured by my accident. But it's not that clear that the law that we have now are going to work well if we think about new technology like cars that are self-driving, for example. Who will be responsible and have to pay damages in the case of an accident there? The owner of the car, the manufacturer of the car, the provider of artificial intelligence. So there are a lot of issues there that need to be discussed. And what is important to understand from our perspective is that the way you design these things may have impact on innovation, may have impact on the future technologies that will be developed. Now, if you do a Google search of liability, risk, and innovation, it's very likely that you find as one of the first few hits a reference to the work of Professor Michael Porter. Professor Michael Porter is a leading scholar in strategy at Harvard, and he wrote a book in 1990, a very influential book called Competitive Advantage of Nations, in which he essentially assessed the performance of different countries, typically developed economies, and try to understand, what kind of factors make the country more or less competitive. And one of the key takeaway from his work in relation to the United States is the quote that I have there, that in his view, in the United States, product liability is so extreme and uncertain that it was retarding innovation. And legal and regulatory climate places firm in constant jeopardy of costly and importantly lengthy product liability suits. So his view essentially is that as it is now in the United States, the system of liability is such that increasing the risk for firms would definitely reduce innovation activity. This is a view, by the way, that is fairly common with managers. A discussion with the executive tend to show that they perceive this product liability risk as very high and reducing, chilling, if anything, their ability to innovate. But it's also something that has been kind of shared, this kind of view has been shared also by a variety of legal scholars. There are academic papers in law journals that suggest that the system as it is now is slowing down innovation activity. And it's not just a scholarly view, even in some judicial decisions by courts, you find references to the idea that liabilities that are too high may reduce innovation investments. Moreover, if you go on web pages of associations that are lobbying for reforms of the tort system, in particular that are lobbying for caps on damages the firm have to pay in case of injuries or problems with their products, the typical argument there why we need cap on damages is that these are slowing down innovation activity. So this is a fairly common and I would say the dominant view out there. But if you look at the empirical evidence, if you look at studies that have tried to check empirically whether or not an increase in liability risk actually reduces innovation, you don't find a lot of support for that. First of all, the empirical work in this area is extremely scarce. We are aware of only two papers that have been published looking at this issue. And one of those papers is actually our own work. So there is a paper of Viscusi and Moore that was published in the Journal of Political Economy in 1993. In this paper, they look at essentially manufacturing firms and have a proxy of the liability risk faced by each firm related to constructed using data on insurance the firms pay for possible product liability. And they find that firms that are more exposed to liability risk, if anything, tend to innovate more. And the same thing in our previous work, we look at tort reform or changes across states, introduction of cap on damages, in particular those related to medical malpractice. And we find that cases in which the reform provides more risk to economic agents are related to some greater level of innovation in medical devices. And in both kind of papers, there is this idea that in principle, changes in liability risk may have opposite effects on innovation activity. So on one hand, the argument of Porter makes sense. If you give too much risk of liability to a firm or to an economic agent, the incentive to try new things, to commercialize new products and new processes may be reduced because the uncertainty of the new product may be also associated with greater expectation of product liability, and this may reduce innovation investment. At the same time, though, there is a counterbalancing effect, that is greater liability risk may induce firms to innovate more innovate more in the sense of coming up with technologies that reduce the risk. And in my work with Hong, we call this type of technology risk mitigating technologies. So there is this kind of trade-off out there, and so far the empirical studies have shown that if anything, the positive effects appear to dominate empirically. On average, it appears that a slight increase in liability risk tends to generate more innovation activities. At the same time, though, the argument of Porter, this idea that liability risk, if extreme, may chill innovation activity, doesn't seem also too crazy. And the point then, from the research perspective, is to try to understand then in what kind of environment, in what kind of economic circumstances, in what kind of condition, under what condition should we expect an increase in liability risk to reduce innovation investments. And this is what we do in this paper essentially. We identify an environment in which a substantial increase in liability risk led to a reduction in innovation activity, a quite substantial reduction in innovation activity, and show empirically measure this effect empirically, and also theoretically try to understand what are the economic mechanisms that led to this effect, to try to understand in general what type of environments we should expect this type of negative effect of liability risk on innovation. The empirical setting for our analysis is the medical device industry, in particular the medical implants industry. Medical implants are medical devices that are placed inside or on the surface of the human body. Examples, like you see in the pictures here, include an artificial jaw that is called TMJ, or temporomandibular jaw implant. They include silicone breast implants. They include pacemakers and so on. Implants are produced using what they're called biomaterials. They're materials that have the property of not creating problems if they're placed inside the human body or if they're in contact with the human body for a long period of time. These biomaterials are no special materials most of the times. They're materials that are used in a lot of other applications, and they're typically produced by large firms that sell the same material to a lot of different industries. Just to give you an example of how general the use of these inputs can be, let's take the TMJ, this artificial jaw, that is going to be an important device for our study. One of the key inputs in the production of that is called PTFE, is a type of plastic that is produced mainly by a company called, the large company that is DuPont. The very same material is also used for coating of electricity cables, used for components of the engine of cars, used for parts of the airplane, and is used also for the production of a variety of industrial equipment. So as you can see, is a general purpose input that is used in a lot of different segments, in a lot of different markets. And this idea of general purpose inputs is really crucial for our analysis. So that is important to know. So what happens in this industry, and in particular with this type of medical implants, with these artificial jaws? Well, something happened that we are gonna leverage in our empirical analysis in the 80s and 90s. So in the 1983, a company called Vitek launched in the market this new TMJ, this new artificial jaw that was approved by the FDA on that year. The approval by the FDA went smoothly, and also it was very well received by the industry. There are a lot of industry publications that are positive about that at the time. Doctors use and implant this device in a lot of patients. But then a few years after, bad things start to emerge. Problems start to surface, these things start to break, and this generate a lot of pain and suffering for a lot of patients. The patients start to kind of initiate through with the lawyers class action lawsuit against the producer, but the company Vitek was not a big company and went bankrupt really quickly. In 1990, Vitek went bankrupt, and essentially these patients got essentially no compensation. So at that point, after the bankruptcy of Vitek, something new happened, something that never was done before in the medical device industry. The lawyers of these patients, they decided to try to get some compensation, taking to court DuPont. DuPont was just a supplier of the input used to produce this device, but they had nothing to do with the production of the device and with the design of the device and so on. It was just a supplier, but it was a big company, seen as a company with a lot of cash. So this lawyer, they tried to get some compensation to see whether they could get something for the clients out of it. Litigation was extensive. We're talking about 651 lawsuits involving more than 1,600 implant recipients and their family. And DuPont didn't lose any of these cases. These cases were either settled or they were ruled in favor of DuPont. But just to get rid of this litigation, it costed $40 million to the company, when the amount of money made by selling the material to Vitek was really small. We're talking about a few $1,000. So this was really an important shock to the industry. For 30 years, essentially, these large companies had no problem supplying the medical device industry, in particular the medical implants industry. But after DuPont was targeted by this litigation, the perception of how dangerous it was to sell to the medical implant producer changed dramatically. DuPont in particular reacted by completely stopping to supply these producers. It changed their supply policy, and it said that, we are not going to sell any of our materials, so not just that particular plastic, but any of our materials, to any producer of medical devices if that material is going to be used for implanted medical devices. So if you were using the material for medical devices that are not implanted, something like producing a stethoscope, for example, then there was no change for you. But if you were using a material by DuPont to produce something that was implanted in the human body, then you were essentially facing a drop in supply. A number of other big producers follow DuPont, and estimates suggest that at that time, we're talking about a 60% reduction of supply of materials for people operating in this industry. There was no change for producers of non-implanted medical devices, but there was a big supply shift for those facing, producing devices that were implanted in the human body. So it's a big increase in the perceived risk of liability for upstream suppliers. So what we do in the paper, we try to essentially look at this case, look at this event that took place in the industry through the lens of a microeconomic model to really spell out what are the trade-offs here that are involved. In our microeconomic model, we have an upstream supplier. You can think about that as DuPont. They sell inputs to multiple markets. We have one market that is a small market, we call market A, and the other market, market B, we could think about it as a big market that is capture a lot of residual industries in which the company sells. And this maps very well with our empirical setting, which DuPont was selling the particular input to supply to produce medical implants, but then to a lot of other industries. And the market for medical implants were really small relative to the others. What we assume is that both upstream, so the upstream firm and the firms in market A, can innovate, so they can produce new products by investing in innovation. And we also assume that the products sold in market A can generate a liability cost to firm U, to the upstream supplier, with some probability. So every time firm A sells a product to a customer, that product can lead to litigation that affects the upstream suppliers. Also here is mapped to our empirical setting, in which every time an implant is sold, with some probability there is some litigation risk that affects the supplier of the raw material. So with this model, we ask essentially the questions: what happens if this liability risk increases substantially? And here the model gives us two key predictions. First of all, it tells you that if the increase is large enough, then the optimal strategy for the upstream firm is essentially to foreclose the market A. Okay? It's not worth selling to market A because it's a small market, and if the liability risk is large enough, then you may not make no profits, and therefore you just are better off ignoring that market. Now, if you are the upstream firm and you stop selling to a very small market, this is not going to change dramatically your profits, and therefore it doesn't change a lot your incentives to develop new product and technology. So we should not expect this foreclosure of market A to really increase dramatically or change dramatically the innovation incentives for the upstream firm. On the other hand, for the firms downstream, for the firms that operate in market A, the absence of supply of an important input may have very big effect on innovation, may reduce dramatically the profitability of new products, and that may reduce the innovation incentives. So this is the prediction of the model that essentially have important implication from the empirical perspective. First, they essentially tell us that liability risk can generate vertical foreclosure, can induce a firm to stop supplying a particular sector or market. And here the industrial organization literature has studied vertical foreclosure in a number of drivers of vertical foreclosure, but as far as we know, nobody has noticed before this idea that liability risk can actually generate vertical foreclosure. And the second implication of the model is that this liability risk can percolate through the vertical chain. So not necessarily the firm that is hit by litigation and liability is the one that is more affected by liability in terms of innovation. In this particular case, the model had an extreme assumption that only the upstream firm could receive liability litigation threats, but there is no effect of those on the actual investment activity in innovation by the firm upstream, but the risk percolates through the vertical chain, and there is a big reduction in innovation activity downstreams driven by vertical foreclosure. In the paper, we also discuss, the theoretical structure of the model and examine a variety and discuss a variety of extension to show robustness of the results to alternative modeling approaches. In the paper, we test empirically these predictions of the model using patent data from medical devices. We get medical device patent from the United States Patent Office database. And here the idea is that every patent at the USPTO is classified in one of many very detailed technology classes. So for example, there's a class 623 slash 5.12, that is for corneal rings, another one for nose prosthesis, and so on. And what we want to do empirically is to try to understand whether after the shock that takes place, the change in the perceived liability risk, innovation activity in patent classes that are related to medical implants is different than innovation activity in classes that are not related to medical implants. Now, it's not that easy to classify a patent subclass as a medical implants or non-medical implants class because there are a lot of those. There are more than 2,500 in medical devices subclasses, and not necessarily by just reading the title of the class you can immediately understand whether the technology is an implant technology or not. So how we do that? We do it in the following way. We first of all get from the FDA a list of medical implants technology of devices that are implanted in the human body, and use this list to construct a kind of dictionary of words that tend to describe medical implants. Words like stent, hip, and so on. And then use a textual analysis algorithm to read through the patents, in particular the title, the abstract, and the first claim of patent to see whether we see any mention of these words, and therefore identify patents that are related to medical implants and not. We then, once we classify essentially all the medical device patents in patents that seem related to medical implants and those that do not, depending on whether or not the algorithm finds these keywords, we then look at how many medical implant patents there are in a subclass, and we classify subclasses as medical implant subclasses or non-medical implant subclasses depending on the fraction of patents, medical implant patents in the subclass. We use a cutoff of roughly 80%, that is the top decile of the distribution, but we show in the analysis that there is a robust to using alternative cutoffs. Examples, show that the algorithm seems to get right patent classes that are implanted or not. So, for example, if you get a class like implantable human bones, our algorithm tells us that 97% of the patents in this class appear to have terms that are related to medical implants. Whereas if I look at surgical instruments for depilation, only 3% of these patents seems to be related to medical implant. To validate the algorithm, also we got a team of graduate students with background related to medical instrument and medical science, and they manually categorize about 500 patents for us, and we find essentially not substantial difference between their categorization and the one of the algorithm. If anything, our algorithm appears slightly conservative. So patent subclasses are very detailed, and in fact, about 1.5 patent application per subclass per year is the average. So there are a lot of zeros in some of the subclasses here, and we discuss this in the paper, and we do a number of robustness checks to deal with this. If we just plot the raw data, we see right away some suggested evidence that this shock that took place in 1990 seemed to matter. In the blue line here, we show patenting in non-medical, in non-implant medical device subclasses. As you can see, is increasing over time. The red line is the patenting in the medical device subclasses related to medical implants. Seems to follow a very similar trend compared to the blue line up to 1990, but then it increases much less steeply. Okay. This suggests, that something took place in 1990 that reduced the growth rate of innovation for medical implants technology relative to the other technologies. And we test this more formally with a series of difference regression. in which we have essentially as dependent variable the number of patents in the technology class. And we look at the difference before and after 1990, and our treatment group are the patent subclasses related to medical implants. The shock is 1990 is the year in which Vitek gets bankrupt, and is the year in which DuPont essentially starts receiving this unexpected litigation. The theoretical model suggests that in this industry, you should expect a negative effect on innovation. So this coefficient beta here, that is the key estimate of interest, should be negative. There are econometric concerns. In particular, there is a concern of having some kind of unobservable variable correlated with patenting in implant or non-implant technologies that generate a change in activity after 1990. To deal with this unobservable, we do a number of things. First of all, we drop from the analysis the patent subclasses related to the artificial jaw. It was really the technology class that was like the one that started this shock. So for the other technology classes, it's much more exogenous, the shock. We also drop breast implants patents because those are also classes in which there was some litigation related to product liability at the time. So we want to really remove any of those classes in which product liability was really the central thing, and we just use the other classes in which essentially this exogenous shock took place in 1990. We provide in the paper a number of anecdotal evidence showing that this change in liability risk was really unexpected. We have a quote here from an interview where we did with one of the senior counsel of DuPont at the time, a person who was really involved in these litigations. And he said that this sort of mass tort product liability litigation against a raw material supplier was unprecedented and unexpected by the medical device industry and biomaterial suppliers. We also provide quantitative evidence supporting the idea that the shock took place in 1990. You see the DuPont litigation related to this type of medical devices, and also the media coverage of these events just started there. Is not, there is no kind of clear pre-trend that may bias our analysis. So here is the baseline result of our difference in differences. As you can see, a drop in patenting in medical device subclasses related to medical implants relative to other medical device patent subclasses after 1990. If you look at the coefficient, the estimate suggests a decline of roughly 35%. The result is robust to changing the cutoff that we use to define a patent subclass as an implant or non-implant subclass. We have a lot of robustness checks in the paper, changing the empirical model, changing the dependent variable, dropping subclasses that are harder to classify, and also various way of treating the standard errors of the regression. We show the timing of the effect. We examine the timing of the effect. There is essentially no evidence of pre-trend before 1990, and then there is a gradual decrease in patenting activity, so it's not a sudden jump. And this is consistent with the industry accounts that this took time to take place, so that there was not just that, from one day to the other, you just had no access to your input, but it took some time for the company to implement this vertical foreclosure. One thing that we examine quite in detail in the paper relates to the possibility of substitution between technologies. So if you think about it, if you're a large medical device company, for example, like Medtronic, that produces both medical implants and non-medical implants technologies, the shock may have induced you to simply switch your research intensity from producing new type of medical implants to producing new type of non-medical implants. If this substitution takes place, it's important to know how big it is, because it means that it's not that total innovation goes down, it's just that there is a substitution innovation activity from one type of technology to another one. We do a number of things to try to estimate the magnitude of this. We drop large firms the patent on both type of technology. We lose alternative control groups. Instead of looking at medical devices that are not implanted, we look at pharmaceutical patents, for example. These are patents by typically different firms, and firms that are not it's not possible to think at an easy substitution between this type of project. And results are robust, and we use this result to do some kind of back of the envelope computation and give a bound to the substitution effect. According to our estimates, there may be a substitution effect at play, but it is unlikely to explain all the results. We think it can account for roughly 20% of the decline that we measure in our baseline regression. We also look at whether or not the effect is localized, so it's just driven by very few technology areas, by very few firms. We don't find much, in the sense that, for example, for firm size, it seems to affect all type of firms. It's a bit less severe for the largest firm, and also this is consistent with the industry account that suggested the largest producer of medical devices had a bit more access to the inputs than others, but it was not zero for them. There is actually an effect there too. Also in terms of patent value, there is some small difference. Appears slightly smaller the effect for patents of intermediate value, and we can explain that. We do explain that in the paper, linking it to some managerial theory on Slack resources. One area which we do find some more substantial difference in the effect is between American firms and foreign firms. So here also is consistent with industry evidence, suggesting that this was really an American shock. Okay, if you were a foreign firm producing medical devices, especially if your supplier were foreign, it was much less risky to kind of it was much easier to get the input. And the idea is that, foreign suppliers supplying foreign firms felt that it was much, much harder for lawyers in US to kind of, try to get them to court, because that require, taking to court a foreign supplier related to a producer through a foreign contract. That is quite harder from the legal perspective. So we use this difference in a couple of ways. First of all, we look as a dependent variable only at patenting of the US, and use patenting of foreigners as control, as a way to kind of capture shocks that take place at the subclass level. But also redo the analysis using a kind of triple difference approach that shows that there is a decline in innovation driven by medical implants patent subclasses, but more specifically within the medical implant patent subclasses, the decline is driven by American firm and not by foreign producers. And we use this result in the paper to kind of help us ruling out, or at least reassure that alternative explanation may not, completely explain our results. We redo the analysis also in the paper using a different data set to measure innovation. Rather than using patents, we use FDA application done at the Federal Drug Administration to have the permission essentially to sell a new medical device in the United States. There are two reasons why this is a nice robustness check. First of all, these are measures that are closest to commercialization. You can patent things that are never going to be commercialized, but typically, if you have FDA approval, you start selling this device. So it's a much more a measure of innovation much closer to the product market. Also here, the FDA has codes that tell us whether a device is actually an implant or not. So it doesn't require the use of our textual analysis algorithm to find treatment and control. We used the FDA code to do that. And we find results that are consistent. There's a decline in innovation activity. Also, the FDA reports data on adverse events affecting different types of medical devices. And we can use that as control also to take care of unobserved heterogeneity. But in general, there is a decline in application for commercialization of the FDA for medical devices that are classified as medical implants relative to other medical devices. We use these estimates from this regression to combine them with estimates that are done by a recent paper by Grennan and Swanson on the effect of medical device innovation. They estimate how much surplus can be generated if a new medical device is developed and available at hospitals, and use that to do a back of the envelope computation to try to really estimate how much this drop in innovation activity generated a drop in actual welfare. Okay, we present this back on the envelope computation in the paper. Remember, our theoretical model suggested no effect upstream. So for producer of the inputs, you should expect no effect on innovation. And here, what we do is to look at patenting in polymers and try to identify the polymers that are potentially usable as biomaterials and those that are not, and see whether before and after 1990 there is a change in innovation activity for essentially technology classes involve polymers that can be used as biomaterial and those that cannot. And here we find no effect consistent with the empirical, with the theoretical model. Both at the industry level and also specifically if you look just at DuPont, patented by DuPont, you find no effect. Now, this is what we document in the paper. It is consistent with the empirical, with the theoretical model. You may ask what happens to the industry. Well, things got better after 1998. There was a policy that was implemented by Congress called the Biomaterials Access Assurance Act. This is a policy that helps shielding from liability producers of biomaterials. If they were essentially finding themselves in the same position on DuPont, it would be after this legislation much easier to actually settle and get rid of all this litigation, to get essentially early dismissals of these cases. This legislation was really pushed by the medical device industry. Here I have a quote from Paul Citron. He was the VP of Science and Technology at Medtronic. You can see it says, remedy must be found for which we will provide the protection necessary to assure the supplier will continue to provide materials to manufacturers. Unless such a remedy is put in place, we will experience decline in medical device innovation. So this is also supporting the idea that they thought something had to be done to reduce the liability exposure of suppliers, because this was reducing innovation activity downstream. That is totally consistent with our theoretical model. We do some analysis of this policy. We can show that things appear to get better after 1998, in which this was the year in which the policy was implemented. here is just a plot of the raw data, but in the paper we show with different diff and with triple diff that results suggest the idea that this policy has helped a bit, but the shock was not as exogenous as the case of the litigation of DuPont. So here we're pushing a bit less the exogeneity and the causal effect, but there is some suggested evidence that this type of policy may have helped restoring innovation activity. And this is essentially the paper. So is an analysis of the medical device industry, in particular medical implant industry. We used this shock in 1990 to provide what we think is the first empirical evidence of a negative effect of liability risk on innovation activity. We show that it took place in a very particular environment, in the sense is a case in which a supplier selling to multiple downstream industries gets a shock in terms of perception of liability risk in one of these segments that is served, and the reaction is to reduce the interaction with this segment, therefore not changing much the profitability of the supplier and the innovation incentive of the supplier, but reducing dramatically the innovation activity downstream. So this kind of percolation of the liability risk in the vertical chain. This is not a very unusual setting. It's a setting that is quite common, especially if we think about the new technology, artificial intelligence, for example. There are big providers of artificial intelligence that provide the software for a lot of very different applications. And if there is something that happens in one particular application that increases dramatically the perceived liability risk of operating in that particular sub-market, the natural reaction of the supplier can be to give up supply to that market. That may not really change the incentive to have innovation at a higher level of artificial intelligence, but may reduce a lot the use of artificial intelligence, the application of artificial intelligence in that particular environment, and innovation activity in that particular sub-market or industry or segment. Okay? There is a suggestive evidence that policy that gives some exemptions to suppliers tend to facilitate innovation in the sense of reducing this negative effect the liability can have. But the bottom line, I think, from the paper is that the trade-offs involved are not simple. The link between safety, liability, innovation is complex. It involves a lot of different economic forces, and therefore more research is definitely required to understand these issues. And I conclude here, and thank you for your attention.